In this video, we will discuss about the finite element formulation of a triangular plate bending element. Now, it's very important to remember from our previous discussion about plate theory is that if there is an out-of-plane load or out-of-plane behavior in a certain element and there's a transverse displacement W, then this transverse displacement W, which is at the middle surface of the plate, so the mid-plane, is actually enough to describe the behavior of the entire plate. Yeah, because the assumption is, of course, the shear deformation is negligible, so we can easily say that this is true. So if the displacement model assumed for just for the transverse displacement W is enough to describe the behavior of the entire plate, then it also becomes much more difficult to assume the correct displacement model that satisfies all the conditions and all the requirements of the behavior of this plate. So that means if we have to have a polynomial which represents the entire element or all the different characteristics, we have to make sure that it also contains the constant curvatures of the states, because of this displacement there's also going to be a rotation, which is of course a derivative of the transverse displacement itself. So the displacement function has to be selected in such a way that all these conditions for convergence have to be included inside this polynomial. So the only conclusion I can make out of it is that it's very difficult to choose a displacement model that satisfies all these requirements. Yeah. So of course there are different kinds of triangular elements that have therefore been developed by different mathematicians and different investigators. And of course I'm going to here show you a very simple triangular bending element described with characteristics that you are aware of also from the beam analogy. But in general you will find multitudes of such elements that are present around us and have started from different assumptions for the displacement model. So let's just look at the standard bending element. So if I have a standard bending element which looks like this, of course it has to be it has to have a very tiny thickness, so I'm just going to draw it so you see that there is a small thickness in the member and the other parts you can't see, so I'm not going to draw that. And we have of course we have to have a coordinate axis. So let's say I have a coordinate axis here which is in direction x. Then we have this one which is in direction y, and of course out of plane is direction. It's not very nice. Just draw it like this as direction z. Yeah. So these are the three different local directions in the element. Now at each node, of course, I'm going to consider the simplest element possible. So I will have three nodes. I have I, then I have j, and I have k. So at the three nodes, I will have the coordinates x, I, y, I, x, k, y, k, and x, j, y, j. And finally, I want to describe what are the degrees of freedom at every node. So then at each node of the triangular plate element, I already know I've enforced a condition that there is going to be a transverse displacement. So I have a transverse displacement W. And if I have a transverse displacement W, then I will have the derivatives or the slopes of these displacements about x and y axes, which are going to give me the rotation degrees of freedom of this node. Right? So then I would have 1 degree of freedom here about the x-axis, and then I would have 1 degree of freedom here about the y-axis. So I can easily give it different names, so I can call this W and the other ones something else, but I know that about axis x it's going to be the partial derivative of W with respect to y, and the one with about the y-axis is going to be partial derivative of W with respect to x. So it's very difficult to describe it for particular nodes. So what I'm going to do is I'm going to give them generic names. W is going to be called Q1. Dou W dou x is going to be called Q3. Dou W dou y, which is about x, is going to be called Q2. and dou w dou x is going to be called q3, which is about the axis y. Okay, so these are the terms I'm going to use. So I have q1, q2, q3. Then at node j, I will have q4, q5, q6. And the same way at node k, I will have q7, q8, q9. So then I will have a total of 9 degrees of freedom in this particular element. So of course, I also have to always bear in mind that this q3, which is dw dx, is going to be negative because it is in the opposite direction. Yeah, it's in the opposite direction for if we take positive displacement dw at a distance dx. That means dw dx is always going to be negative. So now moving on. So we've described the entire element, we've described the nodes, the coordinates, and the degrees of freedom that we are expecting a simple triangular plate bending element to have. So now comes the point of setting up the right displacement function. Now we know that it has to take into account all the different degrees of freedom and continuity conditions, and at the same time it has to have geometric isotropy. So what does that mean? To maintain geometric isotropy, we have to take the displacement model such that it has 9 constants for the 9 degrees of freedom. And this is where the Pascal's triangle comes into picture and is quite helpful. It will become very clear when I start writing the displacement function. So the assumed displacement function wxy, because it is in the in-plane direction, can be given as c1 plus c2x plus c3y plus c4x square plus c5xy plus c6y square plus c7x cubed plus c8 x square y plus xy square plus c9y cubed. So see, there are 9 unknowns because I have 9 unknowns also in the system. I have 3 out of plane displacements and 6 rotations that are dependent on the displacements. Now, in order to make sure that I have convergence, I will have to have a double derivative of w partially with respect to x and y, and I should still get some terms, which is the reason why we have a third order as well, right? So we will still be able to satisfy all the boundary conditions. So if we want to write it very simply, yeah, we want to put this in a nice way, then we can write wxy is equal to a certain vector or matrix or vector, whatever you want to say, eta times this vector c. Okay, and the vector c is of course c1 to c9. Simple. So if I want to put eta together, where eta can be written as 1 x y x square xy y square x cubed x square y plus xy square y cubed. Yeah, and if you are thinking about where this comes from, it's basically Pascal's triangle, 1 xy x square, sorry, xy y square x cubed x square y xy square y cubed, and so on. And you can keep building this up if you want to go higher order. Okay, so we can write it easily like this because then it's easier later on for me to express it in a simple way for larger equations. So now I've described w with 9 constants using the terms from Pascal's triangle. I want to follow all the continuity requirements and convergence requirements. So I have geometric isotropy with 9 constants, and at the same time I will be able to have a second derivative of w partially with respect to x and y, and that will also work out completely fine. So now the constants have to be determined, of course, if I want to move forward. That means I need to apply all the different conditions that I know. So to determine C, yeah, basically C1, C2 till C9, I will have to substitute conditions that I already know, right? Therefore, Wxy is going to be equal to Q1, yeah, at node I. We know that. Yeah, this is for node I. Also, the partial derivative of W with respect to Y at xy is going to be equal to Q2, and partial derivative of W with respect to dx negative of xy can be written as Q3, where at x, I, y, I. Okay, that's the condition. The second condition, of course, will then be equal to this to be equal to Q4, this is Q5, this is Q6 at x, j, y, j, and then you will have Q7, Q8 and Q9 at x, k, y, k. So we will have 9 different equations. Of course, you have to find the partial derivative of W with respect to x and y to move forward. And once you are able to do that, you will be able to clearly write down 9 different equations and solve. Now, after you've used all these relations, yeah, we will be able to substitute it back into the strain energy, etc. But in general, we already have done that before, so we know that the strain, the stiffness matrix of the element, or the local stiffness matrix of the element, is given as a volume integral of, so I can write volume integral of B transpose dB over dV, right? Now we have an idea of what the u that will look like. So in general, your u vector will be equal to the shape function times u. So we have the shape functions, we'll be able to do a derivative and get the strains out of it, because we also know how to now describe epsilon xx, epsilon yy and epsilon xy that we need for our relation. We'll be able to substitute it back and get to this value finally. Yeah, that's the reason why I keep asking you to set up a program, because it's much easier once you have a setup of a certain stiffness matrix, of load vector, of displacement vector with the shape functions, and it's very easy to get to the certain stiffness matrix. Okay, so I'm not going to go through the entire derivation, but as you can see, it's quite simple. You understand how this is happening. And finally, of course, if we want to find the global element stiffness matrix, then I have to have a transformation vector, which will give me the final global stiffness matrix. And since it is just analogous to the conditions of the beam, we also know that we can find out the transformation matrix by making use of the UW and the W and the rotations, and we know about which axes we have to transform them. And in this case, actually, it's quite opposite to what we did with the beam. In this case, it will be very clear that your transformation for the out of plane direction doesn't have to be done, because the out of plane direction is Z, which is the thickness direction, and the rotations are actually along the direction X and Y, which will need to be transformed. Therefore, the transformation matrix, I'm just giving a little basic information about this, is that the transformation matrix for a certain node, so if I want to consider nodal transformation, so only for the 3 degrees of freedom at every node, then I know that for W I need nothing, so I will have 1 0 0 1 0 0. But for the rest, I will have to have the same transformations about direction OX and OY. So I can write the direction cosines as LOX, MOX and LOY, MOY. So this will become my nodal transformation. I need to put it together to get a 9 by 9 element transformation matrix, which is going to be a 9 by 9 one, because the U is also 9 by 1, and the stiffness matrix is 9 by 9 for 9 degrees of freedom system. So in this video, I've just given you a very basic outline of what is so different about using a bending element. And the most complicated thing here is actually to start with the right displacement function polynomial. And the rest of the steps are exactly the same as you followed before to get to the stiffness matrix, the load vector, the transformation vector. So I will not discuss those. But now you have an idea of what is the correct starting point. And this is just a very basic element indeed.